Now let's dive into what we refer to as conditional probability. Conditional probability is the probability of event B occurring given the fact that event A has already occurred. So the notation they use is this line. So we're looking for the probability of B given the fact that A has already happened. Now here's how it's defined. We do the probability of getting A and B, and we divide by the probability of A happening. So we're going to use that calculation with our first example, and they did note here that probability of A has to have something besides 0. It can't be an impossible event, otherwise this doesn't work. I'm going to talk about this with my second example, but all they did here is they rearranged this. They solved for probability of A and B, and it turns out that if I want to find the probability of A and B, I can take the probability of A and multiply it by the probability of B given A. So we're going to use that in our second example. Our first example, we're going to use this calculation right here. Usually give information for conditional probability one of two ways, using a contingency table or a tree diagram. So let's start with the contingency table. So we're talking about paying a utility company bill, and they divided it between paying online or paying by mail, and they compared males and females. So here's the numbers that we're dealing with. Now, this table didn't have totals, but sometimes they do, so I thought I would put that in here. So this total right here, this total right here, but they also total them the other way. There are 50 people on this chart altogether. So let's look at the chart itself before I try to do any calculations. This row says that there were 20 males that they talked to. This row tells me there was 30 males, total of 50 people. If I look at it as columns, there were 36 people who paid their bill online. There were 14 people who paid it by mail for a total of 50 people. This does not mean there was 100 people. It's the same 50 people that are separated by gender. So now we have to start thinking about what these mean. There were 12 males who paid online. There were 8 males who paid by mail. 24 females who paid online. 6 females who paid by mail. So we're going to ask some questions about that. The first question was, what's the probability if I randomly pick one of these people, I get a male? Well, we know that there's 50 people altogether, so that's my bottom number. How many males are there? That's why I added this total column. I add those up. There are 20 males. I'm going to reduce this. A lot of you are turning things into decimals or percents. So I have a 40% chance of selecting a male. The next question says, what's the probability of picking a female online? I go to the female online. There are 24. That's what I want to get. We're still talking all 50 people. So it's roughly 50%. Now let's dive into one of these conditional probabilities. I'll reduce this. We're at 48%. Conditional probability says, I'm still looking for the probability of picking a female, but I know that this person paid online. So this part of the chart doesn't exist. We're looking at just this column. So in this column, there are 36 people online. That's my possibilities, 36 people. I'm looking for the females that paid online. Right here, there were 24 females who paid their bill online. And of course, this reduces. We turn it into a decimal, turn it into a percent. That's about 67%. Now, you're probably going, wait a minute. The males are 40%, which means the females are 60%. But how can 67% of females pay this online? We're only talking about the people online. We're not talking the whole group. So of the people who paid online, given that condition, what's the probability that I select a female? 2/3, 67%. If this would have been male, it would have been 1/3, 12 out of 36. It's almost like this part of the chart doesn't exist. Now, watch what happens when I turn this around. I want to now know the probability that somebody paid their bill online given the fact that they're female. Now I'm talking row. We're only talking females. So given the condition that they are female, there are 30 of them. They want to know the probability, if I pick a female, what's the probability she paid online? 24 of them out of 30 paid online. Again, you can turn it into a decimal, reduce the fraction, turn it into a percent, but this is a conditional probability. These first two were just regular probabilities. So that's kind of how we use a contingency table. Feel free to add the totals if they aren't there. This particular chart did not have the totals in it. I added to it. Now, the other way we tend to see these conditional probabilities is in a tree diagram. Now, for this example, they didn't give me the tree diagram. I'm going to have to draw one. Sometimes they will give them to you. Sometimes you have to do it on your own. But this is talking about a senior survey sent out to high school graduates a few years down the road, asking them some questions about their senior year. It turns out that 85% of those surveyed graduated from high school, and of those who graduated, 90% are happy with their current job. Now, of those who did not graduate high school, 60% are happy with their current job. So there are some holes here, but we can figure this out. So let's try to draw this out. I'm going to start with a G for graduated and an NG for did not graduate. It only told me that 85% graduated from high school, so I need to figure out the other 15% did not graduate. Now, you might have been confused by this 90% because only 85% graduated, and it says 90% are happy. It says 90% of those who graduated. So now I'm on this branch up here. Of those who graduated, 90% are happy with their current job. I'm going to use an H for happy. So that means there must be some that are not happy. I can figure out that calculation. That's got to be the other 10%. That accounts for 100% of those who graduated. Now, for those that did not graduate, 60% said they were happy with their current job. That means the other 40% must be unhappy or not happy with their current job. So there's 100% of the non-graduates. Now, I can do some calculations, but let's see if we need them as we go along. The first question says, find the probability that someone is not happy given the fact they graduated. So we follow the graduated, and they're asking of the people who graduated, what percent, what probability were not happy? I filled that in already. This turned out to be 10%. It's sitting there. It's not 85%. It's of those who graduated. So on this arm, on this branch, how many are not happy? So this one says, what's the probability that someone's not happy? I have two different branches to follow. But if I add this and this, 40% and 10%, that's 50%. That may seem like the calculation you do, but that means those who are happy, 60 and 90, that's 150%. So there's got to be another calculation here. So now let's get out our calculators and do some of these. This is that other calculation I talked about. I'm really taking these two numbers and multiplying them. If I take the percentage for graduates, of those, the percent who are happy, and I multiply those two numbers, I'm going to come up with a percentage of happy graduates. And that turns out to be 76.5%. If I follow the 85-10, I end up with 8.5%. If I follow the non-graduates that are happy, multiply those two numbers, I end up with 9%. And if I follow the non-graduates and the not happy, the 15% times the 40%, I end up with 6. Now, take a moment to add those up, since you have your calculators out already. Now I've got 100% of my respondents. Okay, 76% are graduated and happy, 8.5% are graduated not happy, 9% did not graduate but are still happy, and 6% did not graduate and are not happy with their jobs. These numbers apply to everybody. These two numbers only apply to graduates. These two numbers only apply to non-graduates. So we really have to figure out what kind of question they're asking. This is not a conditional probability. They're saying, what's the probability that I pick somebody and they're not happy? So I have to include the graduates and the non-graduates. About 14.5% of the whole population is not happy with their job. Doesn't matter if they graduated or not graduated. It is not a conditional probability, unlike this first one that only was focusing on graduates. Now here's where it gets interesting. They want to know the probability that they graduated and they're happy. So if I think back to when we dealt with probability, we talked about independent, dependent, mutually exclusive events. When I saw this word, that meant I was talking about two events. So think about the probability of being a graduate. Think about the probability of being happy as a graduate. That and told me we're talking about two different events. So I take 85% who graduated and 90% who are happy. We did that calculation. This is 76.5% are graduated and happy. I didn't include these because, yes, they were happy, but they weren't graduated. This one says, what's the probability that they're not a graduate and are happy? So we're talking this branch here and this branch here. There are 15% who were not graduated. Of those, 60% are happy. I did that calculation. I multiplied those already. It's right here. That's 9% of my population. I have a 9% chance of selecting somebody who has not graduated and is still happy with their job. So a tree diagram is one way we do conditional probability. Contingency table is the other way you'll see them.